I'm Gale Banks. I'm in Dyno Cell 2 and I just got one of these. This is the same turbo that's on the engine right now. Actually, Precision Turbo gave us two of them. We had to change a few things to fit the Precision Turbo where the stock turbo was. First of all, we had to change the mounting foot. We installed a TurboSmart wastegate because the Precision Turbo is no longer variable geometry. And this turbo is a 7675. It's much larger than the turbo we took off. But it's got the same peak RPM rating at around 132,000 RPMs. So must be made out of unobtainium. Compressor discharge, larger. We had to repipe everything down into the charge air cooler. And on the intake side, it's pretty obvious. Our mass airflow sensors go to about 60 pounds per minute. Well, we were in that range with the original equipment L5P turbo. So I thought, before we just go over the waterfall, let's just double it up. So now we have a capacity of 120 pounds per minute. And while we were at it, we doubled up our L5P big ass filters. We've got a pretty free-flowing, very low restriction. In fact, you can hardly see these things on the flow bench at 1,000 CFM. There's virtually no pressure drop through them. So big ass works. Heat blanketing, same 4-inch outlet on the exhaust. We had maxed out the stock turbo. So I want to make a comparison between the stock turbo at around 500 horsepower and 3,000 RPM with the Precision 7675 at the same horsepower output. Can we see any difference? So we've got a larger turbo. It's not variable geometry. So there's this big question. What about turbo lag? How well will this turbo respond versus the stock turbo? No one ever talks about what happened to the throttle response. I am dying to see what happens all around. Let's build a little heat in this thing. All right, we've given it a quick once-over. Precision Turbo is on. Everything is shipshape. Let's fire it up, Aaron. Blower system on. Cranking. Oh boy, that thing is sweet on the starter, isn't it? I don't think that thing went 2 revs as it was running. That's very nice. All right. Yeah, okay, we're at 2,300, about 94 gallons a minute. The thermostats are open. Let's get into it. Loggers are on. A lot of guys talk about on Facebook, I see you're running your iDash DataMonsters from out of a truck. You know, these are logging everything that we're doing in here. These are the prime gauges. Those aren't, other than cylinder pressure. So we got rid of the $80,000 data loggers and went to the $400 nominal data logger. These guys are doing heavy lifting. All right, we're going for 510 horsepower to duplicate the prior run on the stock BorgWarner turbo. So 510 at 3,000. There's 490. Oh, got to dial it back a little. Oh, 510, that's beautiful. Creep it up a little bit. That's it, you're there. Around 891 pound-feet, 510 horsepower. That's the torque at the horsepower peak, by the way. Damn near 900 pound-feet at the horsepower peak. I think we got the data. There we go. All right, let's turn off the data logging. I can't wait to get my hands on that micro SD card. Data logging off. It's mine. I want to show you something crazy. I want to show you what 1 second of data on this card looks like. It looks like this. Now the whole thing here is we have 100 channels and we have 20 samples per channel. There's 2,000 pieces of data on this, and it's 1 second in the DataMonster. So to me, I'm a data junkie. This is data nirvana. I boil it down from this to 2 individual columns of data, 1 for each turbo we've tested here on the L5P. The numbers I'm looking at are amazing. I think we're about to learn something here. Let's run through a few here just to get the flavor of what's going on. First of all, the accelerator pedal position dropped 5.3% when we went to the precision, same horsepower. The maximum cylinder pressure dropped about 1% going to the precision, same horsepower. The rail pressure, we ran the same, 2,000 bar, the maximum stock engine limit, but the main injection on time, 4.8% less. The coolant flow rate was the same, 125 gallons a minute, but the BTUs, the heat being rejected into the engine oil, went down 9.1%. The temperature rise of the coolant flowing through the engine from the in to the out and back to the radiator rose 12 degrees at 125 gallons a minute. With the stock turbo, when we changed to the precision, it rose 9 degrees, which tells me there's less heat being rejected to the coolant, but we're making the same horsepower. The BTUs being rejected to the coolant went down over 1,000 BTUs per minute, or right at 11% less heat being rejected to the coolant. It turns out the turbo and the engine exist in a symbiotic relationship. But just like all relationships, some are better than others. After running the stock turbo and the precision, both at 510 horsepower, we used 5% less throttle, 4.8% less fuel, and we rejected 9.1% less heat to the oil and 10.8% less heat to the coolant. But we made the same horsepower. So what's up? Seriously, what's up? Think of it this way. The crankshaft is your engine's power broker. There are deposits, withdrawals, robberies, and mismanagement. The power stroke is the only one that makes a deposit. The other 3 constitute withdrawals, that being the intake, compression, and exhaust stroke. The intake stroke is straightforward. You're running a vacuum pump. It takes power to do that. On the compression stroke, you're powering a compressor, but there's a wrinkle. Ignition occurs before the stroke is completed, so you're compressing the gases, and now you have this explosion going on in the cylinder, and that happens before it gets to the top. So you've got this added parasitic thing or negative work going on as you burn the gases and get to top dead center. And finally, the exhaust stroke pushes out the hot gases around the valves and through the exhaust ports. Included here is the added restriction of the exhaust manifolds, the exhaust piping, and the after treatment equipment. If you're running a turbocharger, you add in any piping feeding the turbocharger from the exhaust manifolds, generally called up pipes. You add in the turbine housing and the turbine wheel. So now I think I'm going to blow some minds. I know this data got my attention. Let me walk you through it. Ambient air pressure was identical on both runs, 14.4. The ambient air temp was up 9 degrees with the precision. And our ambient air density, that's the density your turbocharging system starts with, was up 1.6 pounds, or a little over 2%, 73.3 pounds ambient air density per 1,000 cubic feet for stock, and 71.7 pounds per 1,000 cubic feet of ambient volume for the Precision. So the Precision is starting with less air density. The whole goal here of turbocharging, supercharging, intercooling, even a high-speed ram air intake, the goal of all those things is to increase the air density going into the intake manifold and from there into the cylinders of the engine. Let's start out with our cold air intake. We changed the cold air intake. We doubled up the filtration. We doubled up the MAF sensors. So we cut down the pressure loss by 55% going into the system. We look at every device starting with the cold air intake system as to its horsepower contribution. Air intake systems rarely add horsepower, but they're vastly different in their performance. The horsepower loss through the filters, through the MAF sensors, etc., stock was 11.5 horsepower, and the setup in the engine dyno right now has a parasitic loss of 6.6 horsepower. I look at the air intake system as something that robs horsepower, and we want to minimize this thing. We want to, if anything, bring it from a felony down to a misdemeanor. That's the first improvement that helps the Precision turbocharger. So let's talk about the turbocharger. We'll start with the compressor. We're looking at the pressure built by the compressor from the inlet to the outlet of the compressor. On both turbos, 30.3 pounds for the stock and 30.9 pounds for the Precision. The temperature gain across the compressor, this has to do with efficiency of the compressor. The temperature gain on the stocker is 289 degrees and 297 degrees for the Precision. Looks like the efficiencies of these compressors are right about the same. The density gain across the compressor is what we're looking for here. We're at 75 pounds per 1,000 with the stocker and around 74 pounds per 1,000 with the Precision. Now, these are two vastly different sized machines, but I'm going to give you, just for grins, the turbo speed with the stock turbo, 116,000 RPM, and with the Precision, 92,000. The stocker is getting towards its limit. The Precision turbo is loafing. This you'll like. The horsepower contribution from the compressor, 183 versus 180. So they're just about matched too. The intercooler is a big contributor to horsepower as well. If it's done properly, we're using a marine intercooler in the dyno cell, so it's water cooled, and it's got a heat exchanger made out of cupro nickel, which transfers thermal real well. The inlet temp to the intercooler, both of them are around 350 degrees, 354 for the stock turbo and 375 for the Precision. The pressure drop through the intercooler, all intercoolers scrub off a little boost. The whole idea is to do it in a way that you don't reduce the boost, but you cool the hell out of the air. In both cases here, we're around 1.25 pounds loss. So the density gain across the intercooler is about the same, right at 66 pounds per 1,000 cubic feet. That gives us a horsepower contribution for the intercooler of 161 and 160, virtually a wash. So following the air density through the system, here's where we'd be at if that Precision turbo were installed in your vehicle at 510 horsepower. We've got 3 readings on the DataMonster: ambient air density, boost air density, and manifold air density. Ambient air density, you've got to accept what Mother Nature gives you. In this case, we're at about 71.7 pounds per 1,000 cubic feet. The boost air density is what we've generated through the intake system. It considers every element from ambient air density all the way to the intake manifold. The cold air intake, the turbocharger or supercharger, the charge air cooling, intercooling, and all the ducting. It's all wrapped up in that number. Ambient air density gets multiplied by the boosting system. In this case, the multiple is 2.9. Ambient's multiplied by 2.9, resulting in your manifold air density. Ambient air density plus boost air density equals manifold air density, and we have 208.3 pounds per thousand manifold air density at a nominal 510 horsepower. If you didn't have this boosting system and you were just inhaling ambient air, you'd have roughly 1/3 the manifold air density and make about 1/3 of the power output. And that would suck. So now you know what this would look like with a precision turbo in your vehicle on a DataMonster. But both the stock turbo and the precision on the cold side look about the same. So where's the big difference here? Why is the fuel efficiency so different? Why is the EGT so different? What's going on with the heat rejection to the coolant and the oil? Let's take a look at the hot side. We've got the stock turbo with a turbine inlet pressure kind of reaching its maximum compared to boost. And we've got this, if you will, racing turbo, the precision, just coming into its comfort zone. Turbine inlet pressure on the stock turbo is at 43 psi, and the turbine inlet pressure on the precision is at 23 psi. That's a huge difference. But let's also look at the turbine inlet temperature. Turbine inlet temperature, 1,385 degrees with the stock turbo, and 1,255 degrees. That's 130 degrees less with the precision turbo. So we have 20 pounds less drive pressure, turbine inlet pressure, and we have 130 degrees less EGT. We're making the same horsepower. What the hell? If we look at turbo crossover pressure, we've got 13 pounds more turbine inlet pressure than boost with the stock turbo. And we have 8 pounds less turbine inlet pressure versus boost with the precision. I mean, the difference between those two numbers is 21 pounds. I like to look at it as percentage. In this case, with the stocker, we had a negative 31% turbo drive ratio. That's what we call this comparison. And with the precision, we had a 34% positive turbo drive ratio. This whole thing, turbo drive ratio, is why we're able to make the same horsepower with so much less fuel, so much less EGT. So having all that exhaust drive pressure has a real negative effect. It's corking up the exhaust flow out of the cylinder. If you take a look at this image, you'll see that you completed the exhaust stroke and you're going to begin the intake stroke, and there's still exhaust left in the cylinder. It could not get out. This is what negative turbo drive ratio will do to your engine's performance. You've got this hot, inert gas. There's no more oxygen left. It won't support new combustion, but it's occupying part of the volume in the cylinder, and it's preheating the incoming gases. So as you come down on the intake stroke, you're limiting the air mass that will come into the cylinder. Everything about this is bad. It's so bad, if you measure the volumetric efficiency of the engine, it really compromises the intake flow to the extent that your volumetric efficiency with a stock turbo and all this turbine drive pressure is around 80%. But the volumetric efficiency without this excessive drive pressure, the precision is resulting in an 87% volumetric efficiency. Anytime you have a lower pressure at the exhaust port, than you have at the intake port. That tends to add air density into the cylinder, and that's where you mix the fuel. And it's all about air-fuel ratio at that point. And look at all the positive things that we've done here. We've changed the air-fuel ratio, number one, from 21.6 to 23.8. We've actually put in less fuel and more air, so we're getting even more complete combustion. You've got lots of oxygen there. We've dropped the exhaust gas temperature, which is easier on everything, and we've dropped it to the extent that the piston temperature went down. That's why there's less heat going to the lube oil in the engine. The piston is a major source of heat to the engine oil. We've cut down the load on the coolant. Therefore, you could make the same horsepower on a hotter day and still not overheat. There's nothing negative about this except for one possibility, and that has to do with throttle response. Why do we have variable geometry turbos in the first place? It's all about nozzling down the exhaust gas coming into the turbine volute and vectoring it onto the wheel in such a manner that it kicks the turbo in the ass. Then you open up the apertures, the vanes, for higher flow, like a normal turbocharger, but the vanes are still there, and the mechanism is still there at peak power. The precision turbo doesn't have that. There's nothing in that turbine housing, and it's a beautiful volute, beautiful job those guys did. But you give away a couple of things here. First of all, it's a bigger, more capable turbocharger. It has more rotating inertia. The wheels are bigger. The bearing system is probably a bit bigger, so it's got a little bit more bearing drag. The main thing is there's no variable geometry. We devised a test right here on the dyno to compare the response of both turbochargers. Our accelerator pedal position and its rate of change was the same on both tests. And then we watched the engine speed. We went from 50 horsepower to 320 horsepower, all at 100% throttle. Our air-fuel ratio is 17:1 on both tests, and it's consistent through the pull. To reach the 320 horsepower with the stock VG turbo took 2.9 seconds. To reach the same horsepower with a non-VG larger turbo, the 76-75 Precision, took 4.3 seconds. That's what people call turbo lag. What this test is equivalent to is an acceleration through a gear, a wide open throttle, going from 1,000 RPM part load. In other words, it's as if you're driving along at 1,000 RPM, the engine's making 50 horsepower and you mat it. What we don't have here is the opportunity to do anything in terms of power braking, torque braking, whatever term you want to call it. If you're going to run this turbocharger on an L5P or any equivalent engine on the street, I'd be looking at loosening up the torque converter calibration, which would allow the engine to move through the lower RPM range and get on the turbine, so to speak. If you just put the turbo on and did nothing else, it would be pretty sad. It would be one of those things where you'd wait, and then it'd be like somebody, like God hit you in the back with a 16-pound hammer. The turbo is massively capable, and it turns out quite efficient. And in terms of efficiency, they're both at around, as we talked about, 72-73%. But one is going off the efficiency, and the other one is coming into its own. So what do we get with the Precision? We're burning 5% less fuel, the same power. The EGT is down 130 degrees. The air-fuel ratio is up. The cylinder head volumetric efficiency is improved. It's a little bit laggy, but we can overcome that. So for the next step, I'm going to push this pup well beyond 600 horsepower. Get a little stratospheric. And I'm going to have a guest. A friend of mine's coming out from Louisiana. But if he wants to get in the door, he better bring me one big piece of king cake. You hear that, Corey? You don't want to miss it. It's getting good. All you have to do is subscribe.